Hello, welcome to today's video. Today we're going to be talking about thermal energy, or more specifically, the change in thermal energy. We'll begin, as we usually do, by talking about the equation. So it's delta E, which resembles the change in energy, equals mc delta theta. As I've just said, the delta E refers to the change in thermal energy, and that's always measured in joules. M is the mass of the substance or the object that we'll be measuring, and that's measured in kilograms. C is the specific heat capacity, and we'll talk about that a little bit later on, and that's measured in joules per kilogram per degree centigrade. Delta theta, this is one you've got to remember, but it's the change in temperature. You would expect delta T, but in this case it's delta theta, and that's degree centigrade, or it could be Kelvin. So the specific heat capacity, this is a definition you've got to remember. The definition is probably harder than what it actually is, but the definition goes as follows. The specific heat capacity of a substance is the amount of energy required to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. There is a required practical on this actually, and I'm just going to quickly talk over this because it can come up in extended questions. So when you want to find the specific heat capacity of a particular substance, you're going to heat the substance, usually with an immersion heater placed into a hole in the block. Let's say if it's copper or a different kind of metal, it's a little bit different for water. And then you're going to record the initial temperature, and then after a certain amount of time you're going to record the final temperature. The amount of energy supplied must also be calculated. I'm not going to actually tell you how to do that in this video, that's going to be a later video. From this data, you're going to create a plot of energy supplied against the temperature change, and the gradient of this graph is going to be equal to the mass times the specific heat capacity. And then you're going to calculate the specific heat capacity by dividing the gradient value by the mass of the substance. So we're just going to do a couple of questions. A 500 gram block of copper was heated from 21 degrees centigrade to 75 degrees centigrade. How much energy would have to be supplied to achieve this? I'm going to take the specific heat capacity of copper to be 385 joules per kilogram per degree centigrade. So we'll start as we usually do by remembering the equation and writing that down, and then we're going to assign values to each letter. So M is 500 grams, and obviously that's in kilograms, so we've got to bring that down 2 kilograms, which is 0.5. C, the specific heat capacity, is given in the question, easy enough, 385 joules per kilogram per degree centigrade. And the change in temperature, so this is 75 minus 21 degrees, because it goes from 21 degrees to 75 degrees. That's a temperature difference of 54 degrees. We're going to plug these values into the equation, so it's going to be equals 0.5 times 385 times 54. Simply enough, that's going to give you 10,395 joules. The second question, what would the temperature rise of 2 kilograms of water be when 10,000 joules has been supplied to it? I'm going to take the specific heat capacity of water to be 4.2 kilojoules per kilogram per degree centigrade. Again, start with the equation, and we're going to rearrange to make the temperature change subject. So that's the temperature change equals the energy transferred over the mass times the specific heat capacity. And again, we're going to assign values to each letter. Change in energy, 10,000 joules. The mass, 2 kilograms, easy enough. C, this is something you've got to be careful with. Remember the units, so this is 4.2 kilojoules per kilogram per degree centigrade, so we want to make that joules per kilogram per degree centigrade, so we're going to times by 1,000, so it gives us 4,200 joules per kilogram per degree centigrade. Going to plug these values into the equation, so you get 10,000 over 2 times 4,200. Now this only gives us a rise of 1.2 degrees centigrade. Water actually has a very high specific heat capacity compared to a lot of other things, which may be surprising, but yeah. This results in a 1.2 degrees centigrade temperature change.